Good morning. My name is Oriol Bove, and I am going to present our paper with title Comparison between two types of seismic tests of racking systems. The authors of this paper are also Miquel Ferrer, Francesc Lopez Almansa, and Francesc. First of all, we will define what a pallet racking system is. This structure is basically designed to store products. It consists on beams, horizontal beams, connected to vertical uprights. The beam, as we can see here, is welded to an end plate, which is a folded sheet of steel profile that looks like an L, okay, and it has hooks. Then these hooks are introduced into the upright perforations and then pulled down, and the connection is done. As we can see, this connection is much more versatile than a bolted one, and this is why it is called a speed lock connection. It allows many configurations to be done with only two products. Sorry. When it comes to design, and more specifically seismic design, these two possible strategies are namely followed. First, the non-dissipative strategy. This one is the most employed in pallet racking systems. In this strategy, no damage is allowed, and so we will always work in the elastic zone. No plastification no yielding is allowed. This is the most employed strategy because mainly all the elements involved in the pallet rack are class 4, okay, and the connections are not very ductile, and this is why, and also there's a scarcity of testing in this industry. This is why this is the most employed strategy. Then the dissipative strategy allows to admit damage in parts of the pallet rack. Okay, so in this analysis, we are working also in the plastic zone, and the seismic input energy is absorbed by the damaged parts. As we said, the elements are class 4, so all this energy will be absorbed basically in connections, or in the beam to upright connections, or in the floor connections too. Well, the objective of this paper is aligned with the dissipative criteria. So to do so, we analyze the behavior of the connections is studied with the help of tests. In this paper, two different testing protocols are compared, the ECCS 45 recommendation and also the Castiglioni novel method. Well, here we can see the tested specimens. Basically, the upright, which is the column, is an omega open profile, as you can see, with regular perforations to allow this connection of speed lock connection. And the beams consist of two mutually nested C profiles, as we can appreciate here, that are not welded each other. They are only welded here at the connection, and they also present 2-point welds here at the free end in order to avoid these to separate each other. Here we can see the test markup. As we can see, the upright is fixed to a rigid bank, and a driving jack is used to apply the input force. Additionally, we see here a permanent load of 5 kilonewtons very near the connection. The objective of this force is double. It has two objectives. The first one is to avoid the total pull-out of the connection when pulling upwards, because these tests, some of them will be hugging, the others will be sagging, and others will be cyclic, so there's a need of pulling this. And the other objective is to somehow represent the gravitational action of the stored products. the gravitational action not only in moment, as we can appreciate that this jack does, but also in shear. Here we see the results of the first test applied, which is the monotonic test. And this test has the only objective to extract this yielding limit of the connection, the point where the plastification starts, the yielding starts. Two types of this test will be done. The first one, the hogging. The sign of this test is taken positive, is pushing downwards the beam. And the other one is the sagging, which consists on pulling upwards the beam, and it has this sign criteria, it is negative. Well, for the first cyclic test, which is the one seen here, ECCS 45, 1986 recommendation, it is a protocol of imposed rotation and based on the bounds found in the previous test, in the monotonic tests. It consists of 4 cyclic tests, 4 elastic cyclic tests, and then groups of 3 inelastic tests, cyclic tests also, until collapse. Next, we see depicted the novel method designed by Castiglioni. This method is basically differentiated to the previous one in the fact that here the gravity load is taken into account. This test will also have 4 elastic cycles, as we can see here, and then the inelastic cycles will include this gravitational load. We can imagine here that we are at the starting of one of these inelastic tests. We start by imposing a force due to the gravitational load until achieving this force. Then we apply by displacement controlled branch a positive value of displacement due to the seism. Once we arrive here, we go back again to this vertical force, to this vertical load. We can here appreciate that the value of displacement for this same value of force is different. This is due to the absorbed energy during this cycle. Then when we do the sagging displacement branch, we see that we arrive to a different point. This difference between these 2 points leads to the fact that this type of test shifts the center of the cycle each time more in the hogging side. So the center will shift this direction. This test is not centered here at the origin. Well, the value of this vertical force is taken in terms of percentage of capacity of the connection. 25, 50, 66, 75, never 100%. And all the values taken from these 4 tests are then analyzed. Here we can see how the results look like from after the ECCS test. The moment rotation diagram is this one, centered at the origin. The hogging and sagging value of yield is different, so that's why it is not exactly centered at the middle. On the other hand, the Castiglioni test always tends to go to the hogging side, to the positive values of rotation, because this of this formation FG force. Here we can appreciate that the absorbed energy in the ECCS is much higher than in the Castiglioni test. Also, the number of cycles performed in the ECCS is higher than in Castiglioni tests. And this leads us to the conclusion that the Castiglioni test is more demanding because it achieves the failure absorbing less energy. It is highlighted that in the Castiglioni test, the energy is mainly absorbed in the hogging side, while in the CCS can absorb energy in the sagging side. Finally, we see here a numerical model we've done in order to obtain a first model in order to obtain the first initial stiffness of this test, okay, obtained in this test, and to contrast them. We've done this test under 3 conditions. The first one is the condition assuming that the end plate does not contact with the upright. The second one is that this line at the bottom of the end plate is initially contacting the upright. And the third one assumes that the whole end plate contacts the upright from the first initial time. So as we can imagine, these values of stiffness increase as more contact arises initially. It has sense. Finally, the conclusions are mainly that the Castillon indications led to a higher demanding conditions because less energy is absorbed. This discrepancy can be understood as the Castiglioni testing protocol should be generally preferred as long as it reproduces better the actual operation conditions of racking systems. Yes, because the vertical load is taken into account, while in this ECCS test, it is not taken into account. In a future research, the authors want to make changes in the design of these connections in order to improve the ductility, want to test floor connections, and also to perform simplified numerical models in order to quantify this energy dissipation in a whole structure, in a whole pallet rack structure. Thanks for your attention, and if you have any question, I will be happy to answer them. Thanks.